Okay, for our model of our squirrel cage induction machine, we are gonna start with the synchronous speed, the mechanical speed, and we are gonna see the concept of sleep. So first, let's start seeing what we got here. Because we put a squirrel cage around our rotor, we are gonna have this circuit. So we know that in our stator we have three coils AS, our three phases that are 120 degrees separated. So we have here AS, BS, and CS. And here we have our angle theta. And for A, this theta is 0. Okay? So we are gonna have a magnetic field. In one instant of time, we are gonna have our magnetic field and we are gonna have a conductor that is our squirrel cage. So in an instant of time, we're gonna have that we're gonna have a moving conductor, a magnetic field, and we are gonna have here the length of the conductor. So we are gonna have a EMF induced in the squirrel cage, and therefore we're gonna have a current in our coils, in our inductors in the rotor. And we know that this is just the magnitude of the velocity times the magnitude of the flux density or magnetic field times the sine of theta. And here we have our length of the conductor. So what this is telling us is that if our velocity vector and our magnetic field or flux density vector are in the same angle, so 0 degrees, if there is a 0 degrees angle between these two, we are gonna have no EMF. So here we have, let's see what our magnetic field in one instant of time looks in space. So here we have pi over 2, here we have pi, here we have 3 pi over 2, and here we have 2 pi. So for this coil, in one instant of time, for example, yes, in one instant of time, we know that our magnetic field is gonna look. Here we are gonna have our magnitude, Bs, and minus Bs. Okay, so we know that in our rotor, in our stator, we have a sinusoidal distributed coil. So here we have our stator. Okay, here we have our stator, and we know that we have our coils sinusoidally distributed. So we have here, we know that it gets our dots get smaller until they are 0, and there are crosses get smaller and big here, and then small until we get to 180. So our magnetic field is gonna look something like this in this instant of time. Okay, and this is for our stator. So the magnetic field is going, here we have our angle theta that is moving this way. So our magnetic field is also changing this way, of moving this way. So this is our magnetic field. Now if we look at the stator, me change the color here. We look at the stator, we are gonna see that it's gonna have a velocity in this instant. Now we know that these two have to be different than zero, they can be in the same angle, so and we have the maximum EMF when they are perpendicular. So we are gonna have here our velocity. So we are gonna have an speed of in our magnetic field uh, called omega s. So we have our speed in our magnetic field that's gonna induce an EMF in our squirrel cage, and the in our squirrel cage, the EMF is gonna have currents in our inductors that is gonna also produce a magnetic field. Okay, and down here in the rotor, we are gonna have that this rotor is gonna be moving at a velocity of omega r. So let me just write all of that. So we have omega s, that is the rotational speed of a stator magnetic field in the air gap. And we have our omega r, that is our rotor speed. Okay, so if we look, our rotor rotational speed of rotor magnetic field in the rotor is gonna be equals to omega s minus omega r. And this rotational speed of the rotor magnetic field in the rotor is what we call a slip speed. That is omega s minus omega r. So if we want to get the slip, it's gonna be omega s minus omega r over omega s, and that's what we call s. So for example, if we have an inducted mechanical rated speed, so the induced mechanical rated speed, what is it? Is our omega r, our speed in the rotor, and we said that we call it 1470 RPM, and we have a frequency of 50 Hertz. Okay, so what is gonna be our rotational speed of the stator magnetic field? And that's what in other videos we saw as the synchronous speed. So that's gonna be 120 times the frequency over the number of poles. So we assume that we have 4 poles. So just, well, let me write the equation so maybe you haven't seen the video. So it's 120 frequency over the number of poles, and this is gonna be 1500. So 1500. So to calculate our sleep, we just need to get our 1500 minus our speed in the rotor over our rotational speed of the magnetic field, and then we get that this is 2% sleep. Okay, so that's how we get all the speeds. We have one speed that is the speed of the magnetic field in the stator, and yes, we have the speed that is the rotational speed in the rotor, and we know that we are going to induce an EMF. The EMF produces a current in the rotor, and the current produces a magnetic field, and so we have two magnetic fields rotating, and the difference between those two magnetic fields is going to be our sleep speed, and if we get the percentage, we get our sleep. I hope this helps. That's it.